Today we will cover bungins and hydrostatics. Okay, these are the calculations related to a particular ship. Now let us see. Earlier you have been taught how to represent the lines of a ship. Basically, we had an x-axis, y-axis, and z-axis, and the surface, if I call it f of the hull, one can write in this form. Actually, what we do, half breadth y is written as a function of x and z. This is what we have done before. In fact, this is what we called stations. This is what we called water lines. Okay. In a most general form, the ship hull is represented by a equation of this form. I will go to the next one. Just briefly recall how the section area etc. were done. You had here a plot. Here we had a what we called, this is my y, this is my z. So we call that body plan, and we had here this is my y, this was half, this has been covered long back earlier, how we represent ship's hull. Now what we require is that we require to do a set of calculations for any given hull or for any floating object, which we call set of Bungin curves and hydrostatics. Okay. Now we will take one by one Bungins. This is essentially curve of sectional areas. And vertical okay. Now what does it mean? Now look at my body plan. I had a body plan where I had a given section like this. This is, let us say, station number, let us say 5, some station. Okay, there are various water lines there. What we need to do is that we need to find out areas of this for different water line z's and moment of this about the baseline. This is my baseline. This is what we call center line. So supposing this is my y. So what we need to find out, section area is integration of y dz, because this is my z, from 0, from bottom to some level z, some water line. That means for this is my water line number 1, water line number 2, water line number 3. For each water line, I require to find out section areas. Also, I need to find out moment of this area about the baseline. Okay, that is we can say vertical moment, which is given by y z dz. Why y z dz? Because see, if you took one small strip here of a distance of say dz, then this area multiplied by this distance, which is z, that is z into y dz integrated. That will give you basically up to a desired water line the vertical moment of section area. Okay, once more, let us say that I am taking, say in another color, a line up to this much. This is my z. So section area up to z is going to be this area. And vertical moment of section area up to this z line is moment of this about this baseline. So now what we need to do is that for each station, once more I will have to draw, for each station, for each water line number 1, 2, 3, 4, 5, etc., I will calculate, these are water lines, I must calculate the section area and the moment. That means I have to calculate, you see, for each station for each water line. Then what I do, then let me say that I have done the calculation. Let me say the area that I have found out is, this will be 0 here. Let us say this is my area, this much is my area. Say here this much is my area, here this much is my area in some scale. So I plot this. Okay, that means I am plotting here the section areas. So like that I get a section area curve because I have calculated section area up to this point, up to this level, up to this level, up to this level, etc. For each level, say up to 1 meter or up to 2 meter, 3 meter, 4 meter, I have calculated the section areas. Then having calculated the section areas, in fact I can write it this way, that section area is as a function of z I have got that against each z taken as 0 meter, 1 meter, 2 meter, 3 meter, I have got this. Also I have got vertical moment of the section area at each against z. These two, I do the calculation for all, this is for a given station. So I must do this for all the stations. Okay. When I do that, the plot of this is what is called Buoyancy. We call it Buoyancy. Now let me explain how we, there are two things. One is calculation, how to calculate. One is having calculated, how do we represent them in a plot. Let me say the second one first and then how we calculate. What we do is that in a profile view, I'll draw in a big one. There is a profile view here in a lines plan. This is my profile. That is basically 0 meter buttock line or central line. We have got these stations, you know, AP, various stations are there. These stations. What we do that each station for each water line, see we have got various water lines, we plot here the section areas like this. This will come here, say if there was a water line here, this will come something like that here. So we plot this section areas. We at the same time also often since we have plotted vertical moment, we also plot the vertical moments, but normally we plot the vertical moments on the other side. These are moments. Okay. Now a question will come, why are we doing this? What is the advantage of this? You see what happens now. Let us say that the ship is under this water line. Suppose this is my water line. So I need to find out what is the volume of the ship, the displacement. Now you see what we can do very easily, that I can draw a section area curve. Now I know that at this particular, these are my sections. I can pick up here this value is my section area here. See, this is this. Similarly, this value, because this is my draft here. See, at this draft, if what it means is, if the section is submerged up to this point, then the section area would be this value, because I have plotted the section area here. So I have got this point. Like that, if I do, I end up getting what we call a section area curve. This is my area curve. Now if I find the area under that, this, then I get volume of that. Then area under volume, you get volume. Now exactly same way, now if I want to take the moments, see, I take these moments now, these values, see this value here, and draw curve of vertical moment of section. Then if I now find the area under that, gives you vertical moment of the volume. You see, it is vertical of volume. What happens if you divide this by this, you will get vertical center of buoyancy. This I will explain in the next slide. See, now looking back at that, what we have done, equation form is like this. Section area is integration of y d z. Vertical, is the writing clear? Y z d z. Now along the length, integrate this. Then you get volume as integration of section areas along length this basically means integration of y dz over dx. See, you are integrating, this is my section area, you are integrating along the length. That is exactly what we have done in the previous curve, that I had this section areas, then I have integrated along the length, which gave me this. Remember that this is in meter square, this is in meter. So I have got, what I have got is meter cube, a volume. Exactly same way now, vertical moment of volume is integration of the vertical moment of section areas, that is YZ, DZ, along the length. And now vertical center of buoyancy, or yeah, is going to be, if I call it 2 and if I call it 1, it's going to be 2 divided by 1. This is the purpose of plotting Bongin curve. Bongin curves actually therefore becomes a subset, you may say, of hydrostatics in a sense. You see, the reason people draw Bongin curves, I will for a moment bring back the previous slide. Can I bring it up? Yeah, not. Can you see this one here? Okay, I will bring it back here. What I mean is that, see, that if you plot these section areas along the length, then very quickly for any orientations of the water line, you can draw the section area curve and you can establish the volume under the trimmed water line as well as the vertical center of volume, which is nothing but vertical center of buoyancy. This is the purpose of doing Bongin curves. So if you look back at Bongin curves here, I will once more bring this one. You will see that you require to keep on doing integration of this type for various water line up to 1 meter, 2 meter, 3 meter, 4 meter. So you will be using all those numerical integration rules that we have taught, 141, trapezoidal, whatever, different rules to do this and this. So you have to do this, let us say for each water line, each section there are say 10 water lines. So you have up to 10 areas and moments, and let us say there are 20 stations. So 20 into 10, 200 such small tables you have to calculate. Okay, so this is a very small work in today's computer technology, but you have to do that. This is what is Bongin curves. Okay, so having said that Bongin curves, we understand that Bongin curve is nothing but integration of quantities along a section. So I will write, just summarizing. In principle, Bongins represents integration of sectional properties, you may say. You are finding area of the section and vertical moment of the section. So this is basically sectional property. Now comes the next issue of hydrostatics. Okay. This is actually, you may say, it's a set of calculations pertaining to the hull geometry for 8 in future Yeah, this is a very, broad term that I mentioned. What I mean is that, see, typically when you have a ship here, okay, what will happen? Now it is floating under this line. You will want to know number of things. You will want to know that if I put a weight, what happens to the ship? If I put a weight, somebody puts a weight here, what happens? If I take something out, what happens? If there is a shift of weight from here to here, what happens? Whole lot of properties of a ship when there are no waves, the water is still, I want to find out. Okay, and this is what is called a set of calculation that you require as hydrostatic. I like to give a bit more basic information which I give in the other classes. I want to give that because this you may not see generally. See, if you take a section, okay, some body, this is water. Water is still. This is actually air, this is water. I in my class like to put it this way to prove that this is water and this is air, okay. So this is a bird and this is a fish to say that this is water and this is air. Now what happens is you take a point here, take some point here. What is water doing? Water is giving a force here, dF, a small force. What is this dF? This is actually pressure into normal vector when n is actually normal vector. Okay, what is P? P is the hydrostatic pressure given by minus rho g z, or if I call this to be z, I am saying minus because z is positive up, so this is minus z. Now what is the total force F? Is integration of dF, okay, over the surface. This is essentially T n ds over the surface, because dF is Pn, it is a dot product, you may say Pn, okay, and P here is rho z z with a minus sign, ds with n. Now if you look this carefully, you will find out that P depends only on the geometry of the hull, because P is connected to how deep the point is. See, the shape is like that, different z. So P is purely depends on geometry. What about N? Also depends purely on geometry. Therefore, this F depends only on geometry. Okay. This is about the force. Now, if you look at different thing of moment, say I want to see moment. Moment is going to be given by a position vector into dF. When r is some position, supposing there is a force here dF, and I want to take moment about this point P, and then this becomes my r vector. Why I am saying is that even this integration will depend only on geometry. Why? Because dF depends only on geometry for hydrostatically steady ship. So this is a case that happens, and it is very important for us to recognize that under hydrostatic condition, your entire force and moment depends only on geometry. Now why I say this is that in the hydrostatic computation, therefore pertains to calculations related to only on geometry, because what we want to find out is that ship is under water, and water is always steady water. There are no waves, there is no gust of wind right now. As far as water is concerned, only steady water. So whatever force that comes on the hull is only because of hydrostatic pressure, which is determined purely by the geometry. Okay. Now we only want to find out everything of the hull under that condition, and that what happens translates down to a number of integrations, number of quantities purely on the geometry. This is what I wanted to say. We have to understand this clearly, that it is only a geometric feature, and if you could figure out what to calculate, hydrostatic becomes extremely simple. We have in a shipbuilding formalized it. We have done a lot of formalism. I will write down the formalism now, but the principle of hydrostatic is that it is nothing but finding out areas and volumes and various moments under the geometry, because all integrations are geometry dependent. Okay, this is the most critical point. We will tell later on that all my um, calculations depend on find out a position of the hull when the net force is 0, net moment is 0. That is the only condition. To find out that, I need to find out forces. To find forces, I need to find out integrations. Integrations are all under geometry. This is the most fundamental point of hydrostatics that we must recognize. In fact, I will tell later on about offshore structure, how they proceed, which is slightly different. See, now coming back to the quantities that we require. First, I will mention about volumes. You need a volume. Okay, this is called volume. This, of course, we have found out that you could integrate the section areas, which is this, over z, integrate over length. This we have done already, because this part is my Buoyancy. We have just done it and you have got this. Okay. Now the vertical moment of volume, let me say vertical let me call it V, okay, just for the sake of this thing. This is given by vertical moment of the sections that I have done already, that is yz dz over z integrated over dx. I have also, this is also coming from Buoyancy. This too is over. Then I have got longitudinal moment of volume. Let me call it L. What that should be? This is, you see, you have to take each section area, which is y dz. This is my section area. Okay, this is my section area here. Now I must multiply this section area with length x and integrate with dx. This, of course, one writes like this: x y dz dx over this. Remember that this part is my section area. So I take the section area multiplied by x, because for any section the x location is constant, therefore I can take it out. See, this full thing is, let us say, for a section number, give an example. Let us say this is my section. Now this section area is this part is this part. Now this is located at distance x. I am taking momentum about this point. So x multiplied by section area, x multiplied by section area, and that I have to integrate along the length. Then I get L. This is the right now I am showing the various integrations. We will talk about how to carry out the integrations using Simpson's rule later part of the lecture. All right. So this is L. Now from this three things we can get number of things. You see, now I can get displacement. We call displacement mass displacement. Okay, in fresh water. This is volume into density fresh water. Just one multiplication. This salt water equal to volume into rho salt water. Just one line multiplication. Now vertical center of buoyancy, as all of you know, this is vertical center of buoyancy. This is given by, of course, 3 divided by this, the volume. This is volume, you see. Okay, this is given by this, what we have done in the last slide. And this, some people write this also as KB. I will explain what is meant by KB in a minute. Similarly, longitudinal center of buoyancy, LCB. This is given by L by V, longitudinal moment by volume. Of course, remember here, measured from that axis about which L was calculated. Remember, this is very important. Because you could take moment from AP, you could take L against AP, you could take L from midship, you could take L from FP. So from wherever you calculate L, LCB, this quantity would be LCB from that point. See, for example, if you took this as everything is X from here, then your center of buoyancy that you get measured from here. But on the other hand, if you take X from here, from midship, then it will be from midship. So this we will explain as I go in the next slide about the calculation part of it. Okay. Let me see a little bit of. Now let us probably see one small calculation of how I can calculate this parts by means of a Simpson's tool. See, let me say that I have a station number here. Okay, I have section areas. I have vertical moment of section areas. This I had. So this station number are say 0, 1, 2, 3, 4 like that. I have got these numbers. Okay. And I have got also this. Now what I have to do here is that I have to use these weights, W's or Simpson's multipliers, because I have to integrate along the length. So these are, let's say, 1, 4, 2, 4, 1, 2, 4 like that. Then I have got here, see, if I call this column 1, if I call this column 2, if I call this column 3, and here I will have, what will I have? 1 into 3 for volume. Then what I get here, this multiplied by station by 3 gives me my volume. Okay. Once more, section areas are to be integrated along the length. Now, instead of length, I am calling station number 0, 1, 2, 3, 4, etc. Remember, station number XS are given by, if I call this N, this is given by H into N. I explained that in one previous class. If station number is N, Nth station, say 5th station, and the station spacing is H, then it is located from AP at a distance of NH. Right. So I have got this. Now I want to integrate this column, vertical moment. Then I have to have this next line as 2 multiplied by 3. It is, say, I write it here, 2 into 3. That is, vertical moment is this 2. Because I am trying to integrate this values. So if I multiply this with this, I will get the so-called weighted value, and when I add them all up, whatever I get here, this multiplied by H by 3 will give me my so-called vertical moment. Okay. Then of course I have to find L. Now for that, what I have to do is to take these section areas, multiply by the station numbers, this into this. Okay, basically I should multiply this with this, but as I said earlier, H is taken out because it is a common number. So I will multiply station areas into station number multiplied by weights. let me call this to be say 0th column. So here I must have 0 multiplied by 1. See, this to remember is my x into SA, that part I showed in the last slide, multiplied by weight multiplied by 3. This I fill it up here. This is to be seen uh, more slowly. Station number into section areas. Let me see here. I have got this here. This is my section areas. This is my station number n. So multiply this with this. That is integration of, we are doing n into s. So multiply section area with station number. That is the ordinate which I want to integrate. So that multiplied by the weight. That means 0 into 1 into 3. Give me this column. I Simpsonize that. Now here, of course, when I Simpsonize that, remember this becomes this into h by 3 into one more h comes in from here. That gives me my L. Okay, this is how I can carry out the calculation. Once I have got this V, L and H, obviously now the rest part is very simple. VCB, as I said, is V by this, LCB is L by B. So I have got that, and of course these displacements are very simple, that is this into rho, fresh water or salt water depending on the case may be. So this will complete my calculation for volumes, but remember we have to do this for all water lines. That means you have to find out volume up to 0 meter water line, which is 0, 1 meter, 2 meter, 3 meter, 4 meter, up to upper deck, and all the other quantities. Okay. So therefore, let us say that up to this point, let me just plot. Supposing I have a plot here, this is my Z, then I will have a plot of volume. Okay, because I have calculated this value, this value, this value, this value, etc. Now I have a plot of this fresh water. I have a plot of vertical center of buoyancy, which might be looking like something like that. Say VCB. I might have an LCB, LCF, LCB, which may be looking like that. Quite often though, this LCB is taken from midship because it is easier for us to find out. You see, we can say sometime something example is that we say it is 2 meter aft of midship or 1.2 meter forward of midship, etc. Why? You see, suppose the ship was, let us say, 195 meter long. Then if you say from AP, you have to say a number like 92.3 meter from AP. It is not easy for you to see, but it is easier to see if you say 2 meter aft of midship, because most people, I mean ships, we think it will be around midship. So that way we get an idea that it is close to midship, but it may be slightly aft. See, if it is slightly aft, we know that the ship's volume is more towards aft at that draft. Forward means more toward fall, this thing. But this calculation wise is very simple. In the previous one where I took moment from that n, you could take n to be 0 for AP and 1, 2, 3, 4, or you can make midship at 0 and ns going negative to AP -5, -4, -3, etc. and +1, +2. Or you can calculate from AP and simply minus L by 2 you can do. Whichever way you want to do, It's very straightforward, or I will just write it down. For LCB, you could take stations this as 0, then this as say minus say 10, minus 9, like that, and this, you know, plus 10. You can take like this. That way you will get directly from midship. What you have done here is that you have chosen the axis to be at midship, or you can take from here 0, 1, etc. And after finding out LCB from AP, then LCB from midship is this minus L by 2. You can just do L is ship LBP. So it is one line calculation, so there is no problem. I personally recommend or suggest that if sometime better to take from 0, because these people confuse between minus and plus. You see, if you begin to take minus 1, minus 2, minus 5 this way, then sometime in calculation this negative confuses people. But if you can do it, then no harm. Many old books prefer this. Many of the earlier textbook try to take at negative stations, taking midship as the station, but you can take the convention follow differ. In America, for example, they sometimes take this to be 0 and this to be 20. They go opposite direction. See, in Britishers we go from this way forward. Okay, so it is a question of convention. Nothing is lost on that. Okay, so this is about the volume integrations as far as getting the volumes are concerned. In other words, if I look at that, this is my ship here. So I have found out if it is up to this much, what is the volume and where is this centroid located. If it is up to this much, what is the volume and where is centroid located. Like that I could find out. So from the hydrostatic curve, if I know the ship is on even keel and if it is at a given draft, I can go back and find out immediately what is the weight of the ship, displacement of the ship, and where is its center of buoyancy. Okay, this is a very straightforward calculation. Next set of calculation that comes are pertaining to water plane area. That is, I have a water plane area of this. This is my y. This is my half breadth. Okay. Now and this is my x. I need to calculate a number of calculations for the water plane area. Number one is that area of water plane. What is area of water plane? Area of water plane is given by simply y dx over the length. Straightforward, this area. Now I need to find out the center of this. Now you see how many centroid location is there. This is a two-dimensional area. Now I have a center somewhere. Let's say this centroid we call F. Now how many coordinates are there? Essentially I should have x coordinate and y coordinate, strictly speaking, but y coordinate is always 0 because the ship is always symmetric. Okay, so I have only to find out x coordinate of center of this thing. Now that's why I need to find out longitudinal moment of this thing. That is will be given by x into y dx. Why? Because you see, if you take a small area at a location say x here, moment of that about this line is going to be, see, this is y, this is dx, dx multiplied by x. So x y dx, this is the small area, this is that distance integrated over length. So this is my integration I have to carry out. Okay, so this is longitudinal moment. Let me call this here uh, L also, say L of a section area is this. Okay, this is very simple. Why I need that? Because what happened now, x coordinate of centroid, which is normally written as f, or I can say x of f, which I will tell what is called is will become LA divided by AWP. This is called by our language longitudinal center of flotation. Oh. I used here xf to show that it is x coordinate of the point f, that is x coordinate of point f. But in naval architecture and maritime profession, we call that as LCF. This is LCF, longitudinal center of flotation. This is what we call. So we have now shown two integration. One is for area, one is for its first moment of area along the x-axis somewhere, which will give me longitudinal center of flotation. I have called this x-axis, it could be actually here. Okay. Now there are more important two integrations left. This is, once more I will draw that here. Now this is my section, this is my x-axis, you can see. This is my y-axis. We also need to find out moment of inertia I about y-axis. So we may call it IYY. This is by y-axis. See, this is YY. What is that moment of inertia about y-axis? Now this I must explain. Now you see here I have got this. This is my y. This is my dx. Actually, the ship would have had a full length with y this side. So if you take a strip like that, if you take there is a theory that if you take a body like that of distance h and breadth of p, its moment of inertia is given by 1 by 12 of b h cube about the axis. See, if there is a rectangle of height h and width b, then about the center line the formula for moment of inertia is 1 by 12 b h cube. In here I have got a rectangle of width 2y. Remember, this is y, there's this side, there's y here. So there's 2y and the width of dx. So this becomes equal to 1 by 12 of 2y cube into dx. 2y is h, dx is b, integration over length. Okay, this is, if you look at that, it becomes 2 by 3 y cube dx over the length. This is my here I y y. Lot of people call this is a kind of a misnomer for the naval architecture people. People call this as also as IT or I transverse. Actually, this is not a transverse axis, this is a longitudinal axis. But in I must emphasize this point. In naval architecture, we call moment of inertia about this YY or longitudinal axis as sometime I transverse. I, because it is related to transverse stability. Which we will see which we will see afterwards. Okay, so this point I will end the first lecture here by emphasizing very strongly that please recognize that in our literature we will be calling a lot of time I transfers, IT, etc. all books, but IT implies actually moment of inertia about the longitudinal axis. Oh, sorry, I made a complete mistake. This is my x-axis. This is my y-axis. This is my x. So it is essentially this is xx. This was a mistake. Okay, this is ixx, longitudinal axis. Anyhow, so with this I will conclude this first lecture, and we will continue with the other moment of inertia afterwards. Anyhow, they close that, right? Okay.